Many of you will have heard the news that Elon Musk's company Neuralink has recently implanted their first patient with a brain implant. The patient is paralyzed from the neck down, and this brain implant allows the patient to control a mouse cursor with his mind, to communicate with people and send emails, and even to play online chess just by thinking of the moves. So how many people in the world do you think currently have brain implants? We know there's the one from Neuralink. Does anyone think there might be 10 people with brain implants in the world? Probably. How about 100? Show of hands? 100? Okay, people still confident. 1,000? Getting doubtful. 10,000? Anyone? Few hands. So in actual fact, there are over 100,000 people in the world who currently have brain implants. Most of these brain implants are not there to help people communicate or play online chess. They actually provide stimulation to the brain to keep the symptoms of conditions like Parkinson's or epilepsy or other neurological conditions under control. This is a therapy that's known as deep brain stimulation. And what it is, it acts as a pacemaker for the brain to target areas that have been affected by disease, and it tries to steer their activity back to a healthy state. And so here I need my clicker. This is what a typical system might look like. So there's an implanted pulse generator that sits somewhere in the body. There are leads, and at some point these leads enter the skull towards electrodes that stimulate a particular brain area. So let's imagine that we are a patient with Parkinson's disease. In Parkinson's disease, we can expect progressive problems with movement. And when we do manage to move, our movements are affected by shaking, tremor. There are a lot of invisible symptoms as well, motivational issues, some cognitive issues, depression, and one of the very debilitating symptoms that we don't often see is the fact that people have real trouble getting good sleep, even from before some of the other symptoms become a problem. And so while at the beginning, you might be able to keep these symptoms under control using medication, after a while, the medication becomes less effective, and you start losing independence, you start losing quality of life. But now your doctor has told you that you've become eligible for a therapy known as deep brain stimulation. It's not going to cure your disease. It's not going to stop the degeneration. But what you do know is that it gives you the chance to maybe win another 5 years of good quality of life, of independence. So you decide to go for it. You have the surgery. And after the surgery is done, it's the moment of truth. It's time to switch the device on. There's an air of apprehension in the room. The clinician starts turning the stimulation up. And maybe at first you feel nothing, but then a tingling sensation. You try a movement tentatively, and it works. You get up, walk across the room, walk back, and it's as if the clock has been turned back on your disease for about 3 years, maybe 4. And you can see that you've got essentially a new lease on life. You've got some good times ahead of you. It's a good day. It's a day full of relief. But at the end of the day, you get home. And as you want to go to bed, you can't help but think, well, what is this therapy going to do for the terrible insomnia that you've had since the beginning of this disease? Maybe we can skip this. So let's talk about sleep. We spend famously about 1/3 of our lives doing it. And we know, I think most of us will know, that good sleep is actually quite important for our physical health as well as for our mental health. And bad sleep can lead to all sorts of problems, psychiatric, neurological, various other health problems. And if you already have a condition like Parkinson's disease, bad sleep is going to worsen your symptoms and might even speed up the progression of your disease. But as it turns out, most deep brain stimulation research is done during the daytime. It's done on patients who are awake. Most patients are sent home with a therapy that runs on the same settings 24/7. So it turns out that sleeping brain activity is actually very different from the brain activity that we observe during waking. So these are electrical signals recorded from the brain at these different time points. And whereas waking brain activity might seem like quick ripples moving across the surface of a pool, brain activity during deep sleep resembles the slow, big waves in a wave pool. And this is why the deepest stage of sleep is also known as slow wave sleep. And these slow waves are key to what sleep accomplishes for us. So on the one hand, it has cognitive functions. It helps with things like memory consolidation. But on the other hand, it has very important physiological housekeeping functions as well, clearing waste products that otherwise might become a problem by accumulating and damaging the brain. And so how are these slow waves generated by the brain? They arise through coordinated activity of whole populations, thousands, millions of brain cells. So let us step inside that brain. We are all going to be brain cells today, and we are going to make a slow wave. So I imagine that some of you might be aware of a concept known as the Mexican wave. If you're not, essentially, we're going to make a wave travel through the audience by raising our hands in sequence from one side to the next. So let's see if we can do this. I will point. 3, 2, 1. Okay, this is excellent. 1 or 2 outliers, but broadly, I acted as a conductor here, so this was a bit of a cheat, because in the brain cells don't have this luxury of a conductor. They need to propagate the wave by closely listening, looking at their neighbors. So this time, I will be the first brain cell. Please watch me, or please watch your neighbors closely, and only if the person next to you raises their hands, you raise your hand. And let's see if we can propagate this wave all across the audience again. You guys are good brain cells. So obviously we required a bit more coordination here. We needed to look, we needed to listen, and in the brain this coordination happens through electrical crosstalk between neurons. And you can imagine that if you provide a big electrical stimulus to this system at the same time, we might disrupt some of that crosstalk. So we're going to do one last slow wave. But this time I have an electrical stimulus. So now, once again, raise your hands only if your neighbor raises their hand, whether that is because they're propagating a wave or whether that is because they might be catching a ball. This might be a time to put drinks away. All right, so I will point this way to start the wave, please. Okay, you actually were a pretty robust wave, but I saw a little bit of chaos emerging there. But I hope it still serves to illustrate that essentially we want to make sure that we don't disrupt these slow waves because we have the potential to do so with our electrical stimulus. This is why our research group is really interested in the interaction between deep brain stimulation and sleep. We really want to learn to strike a balance between controlling the patient's symptoms during the day, on the one hand, but also making sure that they get a good night's sleep. Now, if you're a Parkinson's patient, it turns out that you're actually pretty lucky, because the settings that were developed during the daytime actually seem not to interfere with sleep too much. And in fact, they seem to combat some of the sleep symptoms that patients with Parkinson's disease face. On the other hand, there are some other conditions where it's even more important to think explicitly about sleep. So I'll tell you about a couple of our projects. This is the device that we work with, and this device was implanted here in Oxford by a neurosurgical team at the John Radcliffe Hospital, at the JR. I should add that this is an investigational device at the moment, so it's only being used in clinical trials and research context. And it was implanted for a condition known as multiple systems atrophy. Like Parkinson's disease, multiple systems atrophy is a neurodegenerative disease, and it also has some movement components. However, a much bigger effect of multiple systems atrophy is a dysfunction of the autonomic nervous system. The autonomic nervous system doesn't get enough credit. It's a part of the brain that accomplishes a lot of things for us without us being consciously aware of it. So, for instance, it regulates our blood pressure, it regulates our breathing rate, it regulates our temperature, sweating, digestion, many, many very important things. And people with multiple systems atrophy suffer from this dysfunction. They've got blood pressure, heart rate drops. It's very hard for them to regulate these things. And so, in this trial, we are targeting a part of the brainstem that is very important in the autonomic nervous system. One other role of the autonomic nervous system is to regulate our alertness levels. And it's also involved in something known as the fight or flight response, which you might have heard of. Now, you can imagine that it's quite a good thing to be promoting someone's alertness during the daytime. In fact, we all probably do it to ourselves by having cups of coffee, energy drinks, tea, etc. So these people just kind of get it for free. But at the same time, we wouldn't necessarily drink that cup of coffee at midnight. We don't want to keep people awake. We don't want them to be in fight or flight mode, when they're trying very hard to sleep. That would just add to their problems. And this is why this implant incorporates something very modern and cutting edge, which is a 24-hour clock. This allows us to schedule therapy according to time of day, so that we can have daytime settings that are going to combat the daytime symptoms, but at the same time have nighttime settings that allow the patients to get sufficient sleep. Now, we've got only a very small number of patients in this trial so far, but the initial results are pretty promising. People get more consolidated sleep, so they wake up less. The sleep that they get is deeper, and during the daytime, they actually feel more awake, less sleepy, and they have fewer unintentional naps. So this is good news so far. Another project that we're working on is deep brain stimulation for epilepsy in children, together with the Great Ormond Street Hospital and King's College Hospital in London. And epilepsy can be a very severe problem. People with epilepsy have seizures, and these are uncontrolled bursts of brain activity that can disrupt people's behavior. They might lose awareness, they might fall over and hurt themselves, they might make uncontrollable movements. And if these are frequent enough, and if these are uncontrolled by drugs, this can have a really serious impact on their quality of life, as well as their potential to live independently. And one interesting property of seizures is that they don't always just happen any time. In fact, I will show you a seizure diary, or a visual representation of a seizure diary of one of our patients. So what you see here is a timeline from midnight to midnight the next day. And we've got about 18 consecutive days here, and each colored square represents a seizure of each one of these types. And what you can see is that there's this big clear area in the daytime where there's barely any seizures from about 7 till 9 in both cases. And then at night, you can see that these seizures are extremely common. So we could use this in two ways. First of all, if we can identify these high-risk times for seizures, we can try to anticipate that in our stimulation settings so that we control the symptoms the most, or provide the most input when it's most needed. The other thing it illustrates, though, is that it's particularly important in these types of epilepsy to work out a way to provide seizure prevention while at the same time allowing the patient to sleep, because they completely overlap. So as we go on with these projects, we learn more and more about the interaction between deep brain stimulation and sleep. We use things like questionnaires, but also wearable activity trackers, like ones that some people here might be wearing on their wrists, and even overnight or multi-day brain recordings. And we think there's a lot of potential in this field, because while bad sleep can be a symptom of psychiatric and neurodegenerative conditions, actually, bad sleep also contributes to the progression of the disease. And so here we really have an opportunity to not just provide symptom control, but to start making a difference in how bad the disease gets or how quickly it progresses. And so while our research for the time being won't help anyone play chess with their minds, we really do hope that it will help many people to have the ability to play chess and do other things with their bodies for much longer.